Session. It's my pleasure to introduce Michael Darnel from Indiana University. He's going to talk to us about quasi-angle varieties and lattice ordered groups.
Well, thank you. Let me get one thing out of the way first. I stammer, so if I get stuck on a word, I will eventually get to it. So I used to tell my students that it was a good way to catch up on their note taking. So, okay. I've been working on varieties of lattice ordered groups in some of the lattice structure of those varieties for many years. And let me just briefly go back. There's about 50 years of results on varieties of lattice ordered groups. Clearly, the variety generated by the integers is the smallest variety. And then Weinberg in '65 showed that any free abelian lattice ordered group is a subdirect product of integers. And so the abelian variety A is the smallest variety. Then Wolfenstein came up with another variety called the normal valued groups. They are basically, to paraphrase the wording here, if you take two positive elements A and B, then the product AB is less than the product of B squared A squared. This is just a translation of that into the literature for lattice ordered groups. Okay. A key thing is the representable L groups. They are the ones that are generated by all totally ordered groups, and they satisfy that if you conjugate the positive part of X, then it stays incomparable to the negative part of X. So. And an L group G is representable if and only if every amenable prime is normal. Basically, you have L subgroups, and then there are convex L subgroups that contain intervals between points. And a prime subgroup is one that where if A meet B is the identity, then either A or B belongs to that convex L subgroup. So by Zorn, there are amenable ones. So, and then if you take the definition for R, you define R sub n to be where you replace the first power for Y by the nth power of Y. And this has the characterization that for every amenable prime M, then it's conjugated back by itself by powers of n. Okay, we can multiply varieties. If you have two varieties, okay, well, if you take a variety of L groups, then there's a maximal convex L subgroup, or yes, of G, which is in the variety. So if you have two of them, two varieties, U and V, you can define the product U times V to be where if you mod out the V kernel, the quotient is in U. And this multiplication is well defined, it is associative, and so powers are well defined. A really interesting feature of this, of the lattice of varieties of L groups is that if you have a variety that's properly contained in the normal valued variety, then there's a finite integer n, so that V is contained in a power of its intersection with representable variety. Okay, then if you look at A squared, well, if you have a variety V that such that A squared is not contained in it, then V has to be contained in some Rn. And this gives us a lot of information about the structure, about the convex L subgroup structure of finitely generated subdirectly irreducibles within V. They have to have n minimal primes, well, that's not true. All minimal primes are conjugate to one another in a finite way. So then, okay, 50 years ago, Martinez defined the variety of weakly abelian. I think he told me once that he thought that this meant that he thought they were very close to being abelian. It turns out they are very far away. But that if you conjugate the positive part of x by y, then that is less than the square of the positive part of x. And then Hollister, about 93, in an unpublished work, defined a WA sub n to be where you replace the y by its nth power. In that case, then convexel, if you take a convexel subgroup, then and you conjugate by y to the n, it stays, it is itself. So, okay. I apologize for all the definitions, but we have 50 years to catch up on, so. Okay, Ln. Now, in that same paper by Martinez, he defined some groups that are interesting, and they turn out to be various groups that satisfy laws of the form where nth powers commute. So, and generalizing that a little bit, if you take L sub mn to be where the nth power of x is with the nth power of y, well, it turns out that you aren't gaining anything new. You just take the greatest common divisor of m and n, and then that's the same as L sub d. So, Riley then showed that if you showed that the intersection of, I actually know it was Martinez, who showed that the intersection of R with Ln is just the abelian variety. Then Riley showed that if you can factor n into k primes, then L sub n is contained in the k plus 1 power of a, but there are examples that are not contained in the kth power. And for any positive integer n, we have, of course, Ln is contained in IWA sub n contained in R sub n. So. Okay, Riley then also showed that if V intersect R is abelian, then it's contained in one of the Ln varieties. So it's quite high. So quite a nice theorem. So. An interesting group that was first defined by Martinez in 72, and then an explosion of work on such varieties happened from about 75 on to about, well, still going on actually, but is that if you have two elements such that A meet any A conjugate by any power of B is the identity, while A is itself conjugated by B to the n, then that subgroup is something called a Scrimger group. And turns out that if n is prime, then that generates a non-representable cover of the abelian variety. In fact, every non-abelian cover has to be of that form. There are three solvable representable covers of the abelian variety, and then Holland and Medvedev showed that there are continuum many non-solvable varieties which cover the abelian variety. So you have the trivial variety at the bottom, then you have the abelian variety above it, and then you have this explosion widthwise for the covers. And so it's not your a typical lattice of varieties. So. And then parallel to what Riley's result, if you have a variety whose intersection with the representable variety is weakly abelian, then it's contained in one of these WACE events. So, okay, and then it turns out that the least such n is the least common multiple of all the k's, so that the scripture k group belongs to V. So, well, okay, so years ago, I began to wonder, why are we just sticking with generalizing the abelian law? What happens if you take the nilpotent law and generalize that? And of course, I do my commutators from the left, so okay, it's better to let people know that. And then my second question is, why am I assuming the powers to be the same? And so that's the next question. You know, if you're dealing with the LN varieties, you can just take the common denominator, and then that's your variety. If you are, but in this, with 3 or more variables, we don't know. So, okay, so, well, now that we're going up to nilpotent, so N sub k is the variety of L groups satisfying the nilpotent law. If you take x1, x2 through xk add 1, you get the identity. E sub k is the variety of L groups satisfying the Engel law, x, and then you repeat y k times, you get the identity. And you know, that gets cumbersome to write, so we'll just write that as being x sub k before y to denote that Engel commutator. Well, of course, it turns out that the N sub k is always contained in E sub k. I'm sorry, the nilpotent k is always contained in the Engel k. And if k is more than 2, the containment is proper. But it's known that if k is 2, they are exactly the same. So, Kim and Rottola proved that for any positive integer k, there exists some other positive integer such that E sub k is contained in the nilpotent F sub k variety. Hollister, back about 86 or so, showed that for any that the nil k variety is always representable. Riley improved that to say that it's not only representable, but it's weakly abelian. And Medvedev then showed that, okay, the Engel k varieties are all weakly abelian as well. So, as I said, we know that the 2 Engel variety is the nil2 variety, that the 3 Engel variety is contained in the nil4 variety, and that the 4 Engel variety is contained in the nil7 variety. So it starts to jump upward. You know, that F sub k grows very, very fast. So, okay, so finally for some things, if you take a word in an L group word U with variables, we'll just simplify the notation. Well, actually sort of makes it more complex, but I think clarifies the picture. That we will use this notation to denote the substitution of the G's for the X's. And we'll use V sub that word to denote the variety satisfying that law. So, okay. That does help later on. So, okay, if you take an iterated commutator, we'll say it's of Engel type if for all the variables x3 through xn, they're either x1 or x2. So, and if you take, then with powers involved, we'll say it's quasi-angle. If taking the powers off, you get angle type. If you start off with an iterated commutator with powers, its anglized form, and I didn't make that term up, by the way, is the form where you keep x1, but you change all of the other variables to x2 if the x is not x1. So you could have the x's farther down, but okay, so, well, a really horrible lemma is that if you take a Scrimger group, basically, then then there is a certain substitution. With these two elements, where if you substitute it into angle type word, then you will not get the identity. And it's just, it really is horrible. I mean, it's one of those things where you feel like you have to prove it in detail because no one really believes it's that hard. So, but it's just calculation stuff. Anyway, so now if you take an iterated commutator with powers, well, then the variety generated by it, intersect the representable variety, has to be a weakly abelian. So that means that convex L subgroups are normal. So that's nice. And there's a proof, but I won't go through it. So, and so of course, since its contained, its intersection is weakly abelian, it's contained in some IWA sub m. If you don't have powers, then you can cut down. It's just directly in the weakly abelian variety. So this extends Medvedev's result to where the first variable can occur any place after the second. So, okay, there's a proof I'll go. It turns out that if you take the angle, if you take the angle law with power, with the same power throughout, then that's in a WA sub n. I'm sorry, we'll go back. And if you take the least common multiple of the powers, and all that you care about is that the first two aren't the same. I'm sorry, that the first variable does not reoccur, then that's in a W sub m. And if n is more than 2, then the Scrimger K sub n group is in that variety. So it's the last power that seems to be the most, have the most influence on some of these results. Proof, well, okay. Oh, yeah, this is why was it n more than 2? Well, if you look at the L23 variety, the greatest common divisor is 1, so you get the abelian variety, and then S3 is clearly not contained in there. So that's easy enough. Okay, so generalized two angle. This is really what I wanted to do, but I got those other theorems. I wanted to put them first. So, okay, so we look where the for the angle variety, we take kth power of A, nth power of B, and nth power of B also, or where we have any variable for the third. So we call the first E sub 2 KMN and N sub 2 KMN because they're generalizations of the two angle law and the nil 2 law. Anyway, so we'd like to know that, what its intersection with R is, its representable rank, what is the least power, so that, the least power so that it's contained in a power of the representable variety. And its disjoint conjugate breadth is how far, what is the least n so that you are contained in a W sub n. So, and okay, when one such variety is contained in another, I haven't had very much luck with that. So, actually, I haven't had too much luck with any of those questions except for the first one. So, it's very clear that the nil2 generalization is always contained in the two-angle generalization. Then you get some technical results. If the last two numbers are the same, then you're in the weakly abelian n variety. And which of course then means that if you take the two-angle K11 variety, it's weakly abelian. So, okay, well, if you start off with the two-angle KMN variety, intersected with R, it has to be contained in the two-angle K11 variety. And it's an easy enough proof. You just do some commutator calculus, and you can show that you always end up with that a to the k, b to the k, b to the n is some commutator of a to the k, b. So I'm sorry, it's a product of conjugates of a to the k, b. So, okay, now, unfortunately, we can't do a similar induction to reduce the K. In fact, the book by Badomura and Rempula says that gives an example of a group in which A to the KBB is the identity. I'm sorry. Yeah, is the identity. Have an extra bracket there. While ABB is not. So you have to do some other things. But it can be solved using, since we're in weakly abelian, there are tricks, and so you show that that actually is the two-angle variety. And so, so for any of these, the nil2 KMN variety intersect R is the same thing as the two-angle KMN variety intersect R is just the two-angle variety. So, then some things that make sense aren't too hard to prove. The two-angle KMN variety is contained in the weakly abelian MN variety, and for any positive integer n, the two-angle 1,1n variety is contained in the weakly abelian n variety. Well, okay, now for some of the representable rank results. The nilpotent 1Mn variety is contained in the square of the nil2 variety. We have that, Ln is contained in the nil2 1,1n variety if and only if n is prime. And nil2 1pp variety is contained in n2 squared, sorry. An interesting result here is that the nil2 p squared variety is contained in the cube of the nil2 variety. And this is, and there are examples where it's not contained in the second power. So this is the best. Also, if you have all the letters the same, then the nil2 SSS variety is the same as the two-angle variety. So, some special results. just playing around trying to find directions to proceed on containment issues. So, the proofs can be quite hard. So some questions that I have though is, well, can we find, K, M, and N so that the nil-2 variety with those numbers is properly contained in the two-angle variety? If you take the variety generated by a commutator with powers, you intersect that with R, is it always the variety without the powers? Is the variety without the powers always a nilpotent variety? And 3 is completely known. Nil-2 is two-angle, and it's you can put what is called the McDonald-1 variety, where you have a y between the two x's. And it's also the variety of commuting conjugates. And for n is 4, let me just go back, sorry. You have 4 cases, x, y, x, 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 y, x, y, for the angle types. X, y, 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 x, y, y, x, and x, y, 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 okay. Jabara and Trousers, I'm probably murdering that name, but showed in 2020 that the XYYX being the identity means that the 3-angle law is true. I can show that the XYXY variety is contained in the XYXX, and then the XYXX variety actually is 3-angle, the same variety. So. Okay, so in any case, without powers, you're always inside nil-4. So, and beyond this, if you have 5-angle or higher, you're getting into places where they don't even know if a torsion-free n-angle group can be ordered or can be a lattice ordered. So it's pretty well far open then. And here are all of the 50 years of results. So that is based on.
Thanks. I have time for maybe one quick question, because we have another session to go to real soon. Any questions?
Yes.
So most of the identities that seem to be defining your varieties are purely group theoretic.
Right.
I see a lot of lattice.
Yes.
I assume all these questions are the answers all known just for groups?
No.
They're open there too?
Let's see. Well, in the case of 3-angle and nilpotent 2-angle and nil-2, nil-2 is probably contained in 2-angle. You have torsion elements. They can be, let's see. Yeah, it's the restriction of being torsion-free that
I see.
cuts down a lot of the noise. So.
So it's actually easier in the L group case, is that?
Yes, actually
All right. Thank our speaker.